Yeah, we are live. Can you hear me, Saurav? We are live.
I can hear you.
Yeah, but Saurav, I think is
Uh,
yeah.
can
Okay, yeah,
everyone hear me?
yeah. We can now. Please start.
Okay, okay, let's start again. Good afternoon and welcome to today's DAA astronomy seminar. It is my pleasure to welcome our speaker, Professor Chris Belczynski. Chris is one of the most prominent scientists in the world, specializing in stellar binary population synthesis. He leads one of the most esteemed groups studying the astrophysical implications of the gravitational wave detections by the LIGO Virgo consortium. Reverse his interests sports of all sorts. These days, he is currently a professor at Copernicus Center in Warsaw, Poland. I request the audience during the talk, if you have questions, please type it in the chat box and I can stop Chris and ask the question on your behalf. After the talk, you can raise your hands or keep posting your questions in the chat box and I will.
Suraf, if I may interrupt, you come and go. I only heard the half of the stuff that you said. What
Well,
should
I
I
think
do?
Saurav is having some connectivity issues. Let me say it on his behalf that actually Chris welcomes questions. He can be interrupted, so it would be a good idea if you raise your hands or maybe write in the chat box. Then we'll pass on the questions, interrupt Chris, and pass on the questions to him. This would help keep the talk a bit lively. So Saurav, I don't know whether he's still connected. So maybe I'll just Chris, over to you.
Yes, I can hear you very well, so it's fine. Can you hear me without any problems?
Yes, sure. You're clear.
Very good. Should I start?
Yes, please go ahead.
Okay. Thank you for a very kind introduction. It was a bit too much, but thank you, much appreciated. We live in a very exciting times being in astronomy. Not only, people are digging deeper into dark matter, we are discovering planets daily, and right now we're discovering black holes and neutron stars for gravitational waves pretty much weekly with help of LIGO and Virgo. So we live in a really exciting times for those discoveries. And in my talk, what I would like to do, I'm not going to go much into introduction of gravitational waves into LIGO Virgo detections. I would like to actually touch on the classical astronomy and try to tell you what we actually ask a question. Have we actually learned something new with LIGO Virgo detections that we did not know from the other branches of astronomy, from electromagnetic observations, or let's say particle neutrino observations? So I will start with summary of 0102 results, and those two observational campaigns of LIGO, which are called 0102, gave us 10 detections of double black hole mergers, so 10 collisions of double black holes, and one collision of that famous collision of a double neutron star merger. So I will focus on double black holes because it's majority of detections, and I will talk about what we can learn from merger rate that LIGO observes, from black hole masses and black hole spins, okay? And you will see progression of how we can actually learn about classical astronomy from LIGO Virgo detections. And then I will move to the newest results. So the second part of my talk, I will talk about the third observational campaign. The results of part of that campaign were just released last week in a catalog that LIGO did publish. I did not have access to that catalog when preparing the talk, but LIGO published several most interesting, curious events from that campaign, which are listed here SO3, GW190412, GW190814, GW190521. And those are all very weird or strange events based on our understanding, standard understanding of classical astronomy and classical stellar evolution. And we'll be talking about stellar evolution because I will work on assumption that the black holes and neutron stars that LIGO Virgo detects are the products of stellar evolution. So I won't be touching on subjects like primordial black holes. And one more thing, I will also be talking about one particular formation channel, which is one of the two major formation channels. So one of those two major formation channels is isolated binary stars. So just, two stars circling each other in some spiral arms of galaxies. And this is in opposition to the dynamical channel on which SUVAR works a lot, when you have a big aggregate of stars in clusters, open clusters, young clusters, old global clusters, even huge nuclear clusters. Then you don't need binaries to actually have two black holes to meet each other and collide. In the case that I will be discussing today, you need a binary system that is born from one cloud, two stars go around each other, each one collapses to black hole, and they collide, and that gives you detection of with LIGO and Virgo. But I will comment on the weight of such assumption on my last slide, okay? So let me tell you how we can actually infer information from LIGO Virgo detection. So the way me and my group are doing that, we use something called population synthesis, and we have a computer model which is called synthetic universe. So imagine universe like shown on this Planck plot, which is filled with stars. You start, with Big Bang, then for about 400 million years, you have no stars, but about 4 million years after Big Bang, the stars began forming in the dark halos. Those are population-free stars without metals, pretty much hydrogen and helium, so-called first-generation stars. But then they explode and pollute stellar medium with metals, and then you have a second generation of stars at redshifts of 10 to 5 to redshift of 2, and those stars evolve slightly differently than population-free stars because they're metal enriched. And then finally, then those second generations of stars explode and pollute again interstellar medium, and you have a current generation of stars of population 1 stars. So in a computer model that we have, that we call synthetic universe, we have such a chunk of universe, we fill that with stars, single and binary stars. We have also ability to fill that universe with global and open and nuclear clusters, but I'm treating that separately, so I'm not touching on that subject today. So we're filling that universe with single and binary stars, and as we go across cosmic time, those stars have different masses, and they keep enriching themselves in metals. And this is important because the more metals you have, the stronger stellar winds you expect, and stellar winds remove the mass from the star. Therefore, as you go with redshift to present, the stars are becoming skinnier and skinnier, and they form less and less massive black holes. And that's very important for LIGO and Virgo, because those massive LIGO Virgo black holes must be therefore formed in the past, okay? Not from current population of stars. Or at least you should say that those massive black holes are formed from low metallicity stars with low amount of metal compared to, let's say, sun. Okay, so we have such a universe filled with stars, and then we evolve those stars forward in time. At some point, those massive stars will collapse to neutron stars and black holes, and some of them will be left in a binary. So we have a black hole neutron star binaries, double black hole binaries, double neutron star binaries, and some of those black hole or neutron star binaries will be close enough that they will collapse, they will hit each other, they will spiral due to emission of gravitational waves. It's a weak emission of gravitational waves and loss of angular momentum, binary momentum. They will collide with each other, and they will collide in some given redshift. So if, let's say, we have an event somewhere at a redshift of, let's say, 0.5 of two black holes colliding with, let's say, mass 30 plus 30, we can use in that synthetic universe a waveform that we got from LIGO, and we know how strong is the signal in gravitational waves. Then at redshift 0, somewhere here, we have a synthetic LIGO detector with LIGO sensitivity curve, which corresponds to the current LIGO sensitivity. And we see whether we see a given merger or not. And that way we can probe the synthetic universe. And how do we infer the physics from such an exercise? So each realization of such a synthetic universe corresponds to one model of input physics. So we have one model of how stars explode and form neutron stars and black holes, how stars rotate, how angular momentum transport is being done in massive stars, how stars lose stellar winds. Those are all issues in stellar astrophysics that are not fully constrained, and some of them are simply unknown. So that way we do, we propagate all the stars forward in time, we measure those mergers, and we compare them to current LIGO Virgo observations from 01, 02, and 03. And if our model agree, we hope to learn something. If they disagree, we may learn something as well. So that said, I probably should take a briefer here. Suvar, are there any questions to that part, or should I move on?
Chris, you can move on. There are no questions at the moment.
Okay, so I'll move on. So I'm gonna go from the model and jump right into the results. And I will try to compare LIGO 01, 02 results. Remember, I told you there were 10 detections of double black hole mergers and 1 detection of neutron-neutron star merger. And I will start with comparison of merger rate density, which is measured by LIGO Virgo in local universe, with model prediction. And I will show you what we can learn from such a comparison. So what I'm showing on this graph here, on the horizontal axis is redshift from 0, from current position of the universe, to about redshift 15, when POP1 and POP2, two stars, second and first generations of stars were starting to form. I'm not including on the picture population-free stars. That's a separate subject, and they don't contribute much at redshift 0. Anyway, if you look at all those color lines, red, blue, and black, all those lines are models from one realization of input physics of a synthetic universe, okay? Let's look at the blue line, and you see that the blue line at redshift 0 shows about, on a vertical axis, it's a merger rate density in units, how many mergers you expect per gigaparsec cubed per year. So for the blue line at lower redshift 0 to about 0.5, you expect about 40, 50 mergers per gigaparsec cube per year. But that merger rate increases as you go to higher redshift, to redshift 2, and then it drops down. For you doing stellar astrophysics, that plot is very similar to a Maddow plot of star formation rate density in the universe. And this is expected because a merger rate is directly proportional to number and mass you have in stars. So this plot for double black hole merger rate density as a function of redshift follows Maddow plot for star formation rate. So now, knowing that, we can compare our double black hole merger rate, which is about 40, 50 at low redshift, with LIGO estimate. And LIGO estimate from 01 and 02, I'm doing comparison with 01, 02 on this slide, was estimated to be between 10 and 100 mergers per gigaparsec cube per year, with a peak of PDF at about 40 or 50 per gigaparsec per year. And that's where our blue line is found, okay? So we have a very nice match here. That's a consistent result. Of course, you would like also to ask, can we get the same match for the same model for double neutron stars? And yes, we can do that. Those two black lines show the same results from the same synthetic universe for neutron star populations. I'm not going to go into the details how those two lines are different, but you may take the difference between those two lines as the measure of our internal uncertainty, how we evaluate the rates. And the LIGO rate, so you see those rates are about just above 100 to about maybe several hundreds of double neutron star mergers per gigaparsec cube per year. And the LIGO estimate is from about 100 to about a few thousand. So we also match double neutron star merger rates. In 01 and 02, LIGO did not detect black hole neutron star merger. Okay, so we don't have a merger rate density, but we have an upper limit. And that upper limit is marked with a red line. It is about 600. I think it's about 600. And our red line shows a black hole neutron star merger rate density from my modeling, and we are at about 10. So we are within a very liberal upper limit. So of course, that upper limit will tighten down when all 3 full results are published, and we'll be able to either reject that model or confirm that model, that at least it's consistent with all merger rates. But now you think, okay, that's great. Stellar evolution is highly uncertain. We have a lot of errors. We have a lot of unknowns, like I said up front. But at least you see that we have at least one model that can match all the rates at the same time. So that's good news. The bad news is that we have many models like this. So that tells you that, okay, we have many models that do not fit those measured rates, so we can exclude them, but we have a lot of models that do the same thing for you. So you're not learning much at the moment. However, all those LIGO ranges, let's say for double black holes, 10 to 100, will collapse down to much narrower regimes. So it already happened with the publication from last week for LIGO 03, that rate range from 10 to 100 was collapsed down to, I believe, 15 to about 50. So it became half the size of what I'm using here. So now I will have to match the rate much narrower than was allowed by 01, 02. So we'll be rejecting more and more models. So that's one good news. Second good news is that LIGO will be reaching with every stage to a deeper and deeper redshift, and it will reach all the way to about redshift of 2 for most massive black holes, maybe even a bit higher. So LIGO at some point will start measuring a rate change with redshift. And you see that all those models that I show on this plot pretty much follow star formation rate. And you see the very basic trend. Those models show the rates that increase from redshift 0 to redshift 2 when there was a peak of star formation rate in the universe. So if LIGO does see such a trend, it's a strong indication that those LIGO Virgo black holes and neutron stars come from stars. And so far, it is only an assumption. We don't know that. There's a lot of people, there's entire community working on so-called primordial black holes that were formed in the first microsecond after Big Bang from density fluctuations. Those are Hawking black holes. And they have no stellar origin, and they should not follow star formation rate in the universe. So let's say if LIGO doesn't notice the trend like I'm showing on that plot, it can actually point to non-stellar origin of the LIGO Virgo sources. So this would be a very, very informative inference here. But right now, we cannot conclude much. We need to narrow down those rates with 03 and maybe 04. Okay, so I'm gonna move to another slide. I'm done with merger. Okay, there's a question.
There are a couple of questions.
Okay.
One is, what is this power law drop-off after redshift of 2?
This drop-off is exactly the drop-off observed for star formation rate density in the high redshift universe. This comes directly from star formation. That's a Maddow plot. I can point people out to specific links, Maddow and Dickinson, Maddow and Tassos Fragos papers. They use a lot of electromagnetic observations to measure how many stars were formed per unit volume, per unit time. And that's exactly what they observe. And
the low redshift drop-off, is it smaller volume or star formation rate or both?
That's both delay times, which are short, but that's mostly driven by star formation. So if I plotted the star formation as a color line, you wouldn't be able to tell it apart from some of those lines. It would look, well, there would be some changes, of course, because those lines, my color lines are not exactly the same, but there would be very similar shape of star formation from redshift 0 to redshift 15. Okay, so the first order effect is just shape of star formation rate as a function of redshift.
Okay.
Okay. Another question to that part?
Nope.
Okay, so I'm gonna change gears and move to something interesting to all of us, I believe, masses. And I'm gonna touch right now on neutron star masses. I will come back to this some other time. It's not enough time on that. There's so much interesting stuff going on with black holes. So I will be talking about already outdated data, and I will update myself at the end of the talk. But let's talk about 01, 02 era. The things are changing so quickly that within a few months, you're changing the picture of what we understand. So in 01, 02 era, we thought that we have information that tells us that stellar origin black holes would be found in a mass range from 5 solar masses to about 50. So the full picture would look like that in the last few years. Neutron stars would form from about 1 to 2 solar masses, maybe 2.5. We don't know. The most massive neutron star is 2.1 at the moment, maybe 2.3 if you take some controversial radio observations, but about 1 to 2. Then between 2 and 5, there would be a lower mass gap with no confirmed compact objects. Whether neutron stars or black holes, we don't know what they are in that mass range, but there will be no like well-confirmed compact object in that range. Then from 5 to 50, there were about 20 X-ray binary black holes measured in our galaxy and in local group in electromagnetic spectrum. And we're about, those 10 times 2, 10 mergers, so 20 black holes found in that range up to about 50 solar masses. And then LIGO was noting a drop-off at 50 or about 45, okay? And then it is expected, based on the theoretical grounds, that there is an upper mass gap, and I will come back to both those gaps on my next slides, but there is a gap between 50 and 130, but it's purely theoretical. And then black holes could possibly start forming again above 130, okay? So that was an overall picture in last few, let's say in last 5 years. And it was confirmed by LIGO 01, 02 data. How does this compare to the modeling that we do in a synthetic universe and what we can actually learn from that? So let's look at the plot, which is on the left-hand side, and let's just look at the top panel. That panel shows mass of a black hole components that are colliding in a binaries in the synthetic universe, okay? And those masses go from 5 to about 50, 55. The 3 color lines, blue, green, and red, I will come back to those lines in a second, but they give us different ranges of the mass on the upper side. But let's first look at the LIGO data. And LIGO data is marked on that panel with magenta lines. So if I took those 10 LIGO merger detections, so 20 black holes, I could take the mean value of the black hole masses, and the range of those masses would be from about, here you see, from about 7 solar masses to about 50. However, LIGO also gives us 90% credible limits, so I can construct the narrowest distribution possible with a 90% credible limits, and that's showed by a narrow line right here. That's a 90% narrow. If I take the widest possible range of the black hole mass distribution observed by LIGO 01, 02, I get 90% white line. So that goes from about 5 solar masses to about almost 65, almost 70 solar masses. So depending which error bars I'm using, 9% error, 90%, I'm sorry, 90% narrow, LIGO mean, or 90% wide, I can already exclude some models. And those models have only one thing that is changing. I'm just changing that upper mass gap lower limit, that 50 that corresponds to the green model. I'm changing the physics that sets the lower limit of that upper mass gap. And I will come back to that physics. That upper mass gap is connected to per-instability supernovae, and I will have one slide on that later on discussing all 3 results. But having those kind of wide changes in LIGO errors, I cannot distinguish between those 2 models. But already with all 3, when those ranges will collapse to much more narrow ranges, I should be able to distinguish models that will tell me something about per-instability pulsation supernovae, which is fully unknown on observational grounds because we haven't seen one yet, or we don't know that we detected one. Okay, and I will come back to lower mass gap as well. Lower mass gap is connected not to per-instability pulsation supernovae, but to core collapse supernovae. And it also can give us something that we cannot get from electromagnetic observations. But I will come back to this as well. But right now the masses, already are starting to give us information about supernovae and formation of neutron stars and black holes. So I'm gonna leave it behind, and I'm gonna go to the final part of my 01, 02 discussion of 01, 02 results. I would like to talk about black hole spins. So LIGO, so far, by the way, any questions to masses?
No,
okay.
Chris.
No, okay. We'll move on to spins. So this is the most interesting case that we actually learned something very interesting from LIGO. Black hole spins. So black hole doesn't really measure, doesn't see directly black hole spin. It measures something called effective spin parameter, which I'll call chi effective. The definition of the spin parameter is given down at the bottom of the screen. It's a combination of black hole masses, black hole spin parameters, the spin magnitude. Spin magnitude is defined as the angular momentum of a black hole divided by mass of black hole squared. So J over mass of black hole squared, it's dimensionless. okay? And misalignment angles of those black hole spins in respect to binary angular momentum. So you can think about that parameter as a projection of black hole spins on the binary angular momentum axis. So that parameter, if the black holes are spinning maximally, if the spin parameter is 1, if both black hole spins are spinning maximally and the black hole spins are aligned with binary angular momentum, so if binary angular momentum is pointing towards the ceiling, both black holes are fully aligned as expected for binary evolution because stars form from the same stars, same cloud, same angular momentum, then the spin parameter, effective spin parameter will be +1. If you misalign both those spins by 180 degrees to binary angular momentum, the parameter is -1. If those spins are very big and you put them in binary orbital plane, those cosines are becoming 0. Misalignment angles, are 90 degrees, and that chi effective becomes 0. So the full range of the parameter is from -1 to +1. Okay. So what people expected? People expected, based on X-ray binaries known in our galaxy, that black hole spins will be kind of large, 0.7, 0.9, even almost 0.99. And then you would expect, if those spins are aligned, that the chi effective will be, +0.8, +0.9, maybe even +1, will be at a high value. But this is not the case. Look at the picture, any plot, left or right, doesn't matter, but look just at the blue stars with error bars. On the horizontal axis, I'm showing effective spin parameter from -1 to +1. And all those 10 LIGO detections are shown with blue stars with the associated arrow bars. For those stars, the vertical axis does not have any meaning. The vertical axis has only meaning for my models, to which I will come back in a second. But when you look at those stars, they are almost all consistent with effective spin being 0, okay? And they are the same points on both plots, okay? So what does it tell you? It tells you one thing: if spins are high, if spin magnitudes are high, you need to take all those 10 binary black holes and you need to put both black hole spins in a binary orbital plane, or they need to be just exactly the opposite, so they cancel out. This is highly improbable and I cannot think of a good mechanism doing that for all of the LIGO detections. So it's hard to imagine, although it's not impossible. You can play with triples, you can play with some various stuff, and you can try to do that. But I think the more natural idea is, can you make that chi effective close to 0? You just make spin magnitudes A1 and A2 close to 0. You just make a slowly spinning black holes, and then chi effective becomes naturally 0, no matter where the spin directions are. Whether they are totally random or aligned or misaligned, doesn't matter. Spins magnitudes are small, then chi effective are small. So this gives us a nice lesson. So how can we actually predict a spin of stellar origin black hole? So you do this following. We know from observations the rotation of massive stars, okay, with some errors, but we do know that. Then the stars rotate, it evolves, and then it collapses to a black hole. Those massive LIGO black holes, we think they collapse in entire thing that is left from evolution will probably collapse to black hole. There's no mass ejection, so probably not much of angular momentum loss. So this is not an issue of supernova explosion or core collapse. You don't lose much of angular momentum at the end. But what happens during evolution, you may have angular momentum being transported from the center of the star to the outer layers of a massive star via unknown mechanism, because we don't know what would transport angular momentum in massive stars, and then you can blow that angular momentum away through stellar winds. And stellar winds, we also kind of know, or we have a good predictions how stellar winds should work and how much mass and angular momentum they should take away from star. So we created two synthetic universes. In one universe, we use the same rotation, same core collapse model, same winds model. We just change one thing in each model. One model, we assumed a very inefficient angular momentum transport, which is shown on the left panel. There are two models, but with the same with the same angular momentum transport. Let's just look at the red line, okay? And that's called Geneva model. The angular momentum is transported by meridional currents. Doesn't matter the details, I can describe them later. But this is very inefficient momentum. So you keep a lot of rotation in the stars, and when you collapse to black hole, you have a lot of momentum, your black holes are highly spinning, And the result is that that red line is the model. That's a chi-effective of emerging black holes detected by LIGO in our synthetic universe as we see them in the synthetic universe. And now vertical axis is very important. It shows the detection probability. And this is logarithmic plot. And pretty much you see a huge peak at chi-effective about 0.8. That is what is expected for aligned black holes with high spins. This is totally inconsistent with what LIGO and Virgo detects. So you know that those meridional currents that were used in many stellar models for last decades are totally off the table. They don't work. Okay, so we did change model, we went to the other side of the equation. We just went opposite. We just asked, okay, let's take the very efficient angular momentum transport mechanism in a star, which is done through magnetic dynamo. Let's transport the angular momentum to the stellar surfaces, blow it away with the wind, and then collapse stars to black holes. We can calculate angular momentum. Let's plot effective spin in that synthetic universe, and let's look at the red line again. And you see the red line, it's again detection probability logarithmic, so it peaks at about 0.1, not at 0, but at about 0.1. And this is now fully consistent with those blue points, especially taking into account error bars. So this tells you that most likely those black holes were formed from stars and that magnetic dynamo transport angular momentum very efficiently in massive stars. And this is huge news because you cannot measure angular momentum transport in massive stars. Okay, a lot of people would mention astroseismology. You're right. You can do astroseismology, but not for those huge massive stars, which are black hole progenitors. Those are 50, 100 solar mass stars, very chaotic, very fuzzy atmospheres. So you cannot do precision photometry and look into a rotation of the star into the center like you can do for sun. You cannot do that. So you don't have any other means to measure angular momentum transport in those stars. So we have learned something here already from 01, 02 about inner workings of massive stars. So that's a good news here. So I'm gonna stop with 01, 02 here. Any question to that part, or should I move to 03?
So I actually have a question. Can you comment on the uncertainties related to the magnetic dynamo, and so how much modeling is needed there, and what is known and what is not known?
Okay, so that's a very good question. We have several models how magnetic dynamo may work. And actually this model that I'm showing here, it's kind of average magnetic dynamo. It doesn't work too hard. Actually, some people claim that based on astroseismological data for lower mass stars than black hole progenitors, like 5, 10 solar mass stars, magnetic dynamo should be more efficient, even than I'm assuming here in those models, so-called Fuller models. Okay, so in this model, black holes form usually with typical spin parameter A of about 0.1, 0.2. In those other models, they would have almost no spin. The spin would be 0.01. Okay, and when I put that model into synthetic universe and do a test which model fits the data better, both models fits the LIGO Virgo data about the same. I need more points on the plot. But to answer your question in terms of numbers, think about black hole spin changing from about 0.01, so like almost zero spin, to about 0.1 in terms of magnetic dynamo uncertainty on a black hole spin. Does this answer your question?
Yes.
Okay.
And there is another question. What's the difference between fallback kicks and high kicks?
Okay. So as you see in chi-effective spin definition, I have cosines of black hole misalignment angles, and those are set. All my stars that will form black holes will be fully aligned. So those cosines would be 1. Okay. But what can misalign them, changing chi-effective, is a black hole natal kick. For the red models on both plots, I have used the model that black hole kicks are very small. So pretty much most of the black hole spins are aligned when they merge. However, we don't know that. We have a very little knowledge of black hole spins, very little constraint. So if I give black holes high neutron star kicks, like as high as for neutron stars, hundreds of kilometers per second, I disrupt a lot of black hole binaries, but a lot of them will be misaligned. kind of similar to what you could expect in a dynamical channel formation when spins are kind of random. Well, of course, they're not fully random in my channel, but the definition, the distribution would look different. And pretty much that's shown with magenta lines. So if you look at the left plot, you see that that peak at the high chi effective is not as prominent for high natal kicks as for low natal kicks. So I'm closer to the data, to the blue data points with high natal kicks, but still far away from them. We did some good tests whether that magenta distribution can match blue points, and no, there's no chance for that. While for magnetic dynamo, both models do match LIGO points, okay? So that's how I treat natal kicks. We have several such, parameters that we can change and try to match the data. Did that answer the question?
I think yes.
Okay. How much time do I have? Do I have 20 more minutes? Or no,
Yes,
I have
you do.
less time. I don't want to take too much of your time. Okay, so let's switch gears and let me discuss, maybe not all of them, but two. I wanted to discuss three, but let's discuss two, not to bore you with all those tiny binary details, but let's discuss two most interesting double black hole mergers from O3. So the first one was GW190412. And on the right-hand side here, I'm showing LIGO Virgo parameters. This was the first unequal black hole mass merger. So to put it other way, all 10 01, 02 LIGO black hole merger were consistent with having two black holes of exactly the same mass, okay? They were, mean black hole masses were different, but within error bars, they were consistent with having black holes of exactly the same mass. But this one is totally different. So LIGO measured one mass at about 30 solar masses, and the other one below 10 solar masses, about 8 solar masses. LIGO also measured the frequency of such mergers within entire double black hole population. So LIGO measured that such double black holes with mass ratio below about 0.4 should constitute about 10% of all double black hole mergers. And then it measures quite credibly also effective spin parameter to be somewhere between positive plus 14 and positive plus 34. Okay, so it's not such a small value, but still probably consistent within 3 sigma with being 0.1 or so. And then now there were two other measurements. The spin magnitude of the first component, which was claimed pretty high, and possibly that the precession parameter was also high, meaning that possibly black hole spins are highly misaligned. However, those two measurements were really dependent on Bayesian analysis and priors that LIGO did put into the analysis. So I'm gonna base my conclusion on those first three red measurements: masses, frequency, and effective spin parameter, although we can reproduce those as well. So now, why this event was interesting? Because in both channels, in isolated binary evolution, of which I'm talking today, and dynamical channel that others people work on, typically the black hole forms with almost equal, with mass ratio close to 1, with almost equal mass black holes, as was observed for 01 and 02. So nobody was asking a question about mass ratio distribution during 01, 02. However, it doesn't mean that we don't have an equal mass ratio double black holes in our simulations. We do. The question is, do we have such systems that would resemble GW190412, and do we have enough of them? Do we have 10% of them? So to answer the first question, on the left-hand side plot, I'm showing a typical system that was found in our existing simulation, system formed at low metallicity, two massive stars, 80 solar mass and 40 solar mass star. We go through mass exchange, common envelope, one star collapses directly to a black hole, another explodes in supernova 1bc. I'm not going to drag you through all those details. There's a paper out by one of my students, Alexandra Olejak, on the details of its system. But in the end, that system, we can reproduce not only just all those 3 points, but all 5 points. We can get all of them. The question is, can we get enough of them? The point number 2. So I'm going to spend next slide just showing you that, yes, this is possible within our standard evolutionary assumption. So let me show you this plot. And for the model that I was showing, the synthetic universe model, I'm showing cumulative mass ratio distribution. And mass ratio is defined as a mass ratio of a lower mass black hole to a higher mass black hole. So it's always lower than 1, okay? So the extreme mass systems will sit at the lower mass ratios. Here at 1, you'll have equal mass systems. And you see this is a percentage fraction of systems with mass ratio smaller than given value, and it's a logarithmic plot. So most of the systems will sit right here at the high mass ratios. Pretty much we observed that, for about 80% of double black hole mergers in our model have mass ratio higher than 0.5. Okay, that's about it. And that's what we all had in mind during 01, 02, that most of our predictions, both in isolated Brownian evolution and dynamic evolution of global clusters, most of the mergers would have comparable mass ratios. However, we have a tail that extends to well below 0.2. And we can actually ask the question, that's a red line, we can compare to LIGO measurement, how many systems we have with mass ratio below 0.4? And we have about 9.2%, but LIGO measures 10%. That's a fully consistent. So I'm gonna go back one slide. So I would like to say, I'm not claiming that that system comes from binary isolated evolution, but it's fully consistent with binary isolated evolution. Although I'm sure people can form such system in global cluster as well. So we don't really know where it can come from. But anyway, those systems are expected, and we expect some fraction of those, okay? Now, I'm gonna speed up a bit. I'm gonna skip one system, and if somebody's interested, please email me or so. I will talk to you over email, or maybe I'll give another talk in a month or so on that system, but I will skip GW 190814, which has a object in a lower mass gap, but I will move directly to, I think, the most interesting system that LIGO and Virgo so far has published, which is GW 190521, which has an 85 solar mass black hole and 66 solar mass black hole, both of those black holes being in the upper mass gap. And this probably deserves a minute of historical note that comes to one of the Aspen LIGO Virgo meetings on gravitational waves, when Suvar was taking part of it, I was taking part of it, and we actually did a bet back then, when the highest mass black hole was about 45 solar masses. We actually did place a bet whether LIGO will ever, or within first 100 positive detections, will discover a black hole with 55 solar masses. And on one side, that was Suvar, it was Carl Rodriguez and Fred Razio. They were saying global clusters can do consecutive mergers. They can merge those 40 solar mass black hole. You can catch another 40 solar mass black hole, and then you have a second generation merger or even third generation merger. And you should see those mergers more massive than 55, even if stars do not make them, okay? Such massive black holes. Me, Dan Holtz, and Stan Woosley, which we work on stellar evolution, we said, no, stars are not able to do such black holes, and global clusters are not enough effective factories for production of such second generation mergers. And we placed a bet, and we lost that bet. We lost that bet very quickly, which is great actually for all of us, because it puts science forward. So let me give you a note or at least few sentences, because it's a pretty complicated subject, why we do not expect stars to form black holes in that upper mass gap. So the classical peri-stability mass gap that we knew just before a year ago or so, before we heard rumors about LIGO 100 solar mass black hole, about this event. So the classical limit for that mass gap was between 50 and 135 solar masses. So this is connected to the fact that for massive stars that would form black holes in that mass range from 50 to 135, explosive oxygen burning in a last week of a stellar evolution of that star before it will collapse to a black hole, the temperature of the star is so high that oxygen burning will go explosive. And this happens that those stars are so massive that the photons are so energetic that they change to pairs, to positons and electrons, and the photons disappear because they change to pairs. You remove radiation pressure that supports the star, and star collapses, temperature goes up, oxygen goes explosively and explodes entire star. You have no black hole whatsoever. So that's why we expect a gap. When you go to masses higher than 135 of the inner stellar core, gravity wins over reaction rate energy that you can produce from such an explosion of oxygen burning, okay? So those limit 50 to 135 depended on comparison of gravity and reaction rates that gives you burning of carbon and oxygen, really. okay? So now the story becomes interesting story. People began hearing rumors about LIGO Virgo, massive detections about, a year ago or so. And people began, coming up with the models, how actually we could shift a limit of a instability mass gap or upper mass gap. So right now I'll be talking only about that 50. So we have a classical instability mass gap from 50 to 135. And I'll be talking about how we can shift that 50 upwards so we could feed those two objects that LIGO did detect, 85 and 66 solar masses, to be produced by regular stellar evolution without any help of global clusters. So let's do a bit of not an old history, but right now everything seems to be history. Things are moving so fast. So for population-free stars, for metal-free stars, Worsley already proposed in 2017 that 70 solar mass black holes could be formed from stars. Okay, so we already can explain the lower mass object in GW 1905-21. Okay, this year, Wing et al., Jorik Wing, about a month ago, 2020, has pushed that limit for population-free stars to 85. So we can explain both objects with population-free stars. Now, if you look to 2018, you go to population 2 stars, already metal-enriched stars, that limit was moved to 80 in 2018, and was moved to 85 in 2020, by Farrell et al., about a few weeks ago. For population 1 stars, I have moved that limit in January to about 70 solar masses. Okay, that it was playing with, so that was mostly those limits were shifted to higher value due to stellar evolution uncertainties, mostly connected to convection, mixing, and wind, that changes how the oxygen burns in the last week of stellar evolution. We probably pretty much changing the parameters of convection and mixing and stellar winds and dredge up. You change explosive burning to non-explosive burning, and you don't disrupt the star and form a black hole. Okay. So that's one source of uncertainty. Another source of uncertainty is fusion reaction rates, which are highly, highly uncertain for reaction rates that produces oxygen. So if you lower, that comes to pretty much burning, fusion of carbon. You burn less carbon, you produce less oxygen, and therefore you don't explode the star. So if you lower carbon burning reaction rates, you can actually put the limit, that 50 solar masses, you can put those 50 solar masses and push it up to about 90 solar masses. And that was shown by Bob Farmer in 2020, about, I think, a month or two before LIGO publication. And it was then confirmed by Michela Mappelli group, Guglielmo et al. 2020. Okay, so this set, you can possibly form those massive black holes directly from stellar evolution. Now, what I did, I constructed, so this is going to be my last slide. I have constructed one synthetic universe which allows for those uncertainties and allows pretty much for production of 90 solar mass black holes from stars, which will be given, connected to, uncertainties in a stellar evolution and reaction rates. So let's look at such a model and let's see, can we actually reproduce such systems that would have both black holes in that classical per instability mass gap, okay? I'm gonna skip those slides. And here we go. So that's my last slide before the conclusion. I'm sorry, I'm running a bit late, but I'm gonna finish with that. So LIGO Virgo masses, we already know. LIGO also measured the merger rate density of such massive objects. Here are the values, 0.02 to about 0.4 such mergers per gigaparsec cube per year. That's a 90% credible limit. LIGO also measured effective spin of this merger, which is about 0, which is consistent with all O1, O2 data. It goes from about minus 0.3 to plus 0.3. And there was a weak result about potential precession being, high and on positive, well, it's on the positive side. So potential evidence that black hole spins are misaligned, but this is really prior dependent, okay? So now let's see if I can reproduce such a star. So as it appears, if I take a low metallicity model, pop population 2 stars, 2 massive stars, 180 solar mass star plus 140 solar mass stars, going through one Rorschach overflow, through one common envelope, two black holes collapsing directly to, two stars collapsing directly to black holes, I can reproduce all the three basic parameters. I can get masses. That system that is shown on the left-hand side have 85 plus 65 solar masses. Merger rate density is 0.04, so it's within LIGO 90% credible limits. It's not 3 sigma limits, 90% credible limits. On the low side, but within the limits. Chi effective is between 0.09 to 0.3, which is fully consistent with LIGO data. However, I cannot reproduce precession. I cannot reproduce misaligned spins because those massive black holes in my model, they do not get black hole kicks, so they collapse directly and they're fully aligned with binary angular momentum. So I cannot do that. But this week, that result, precession parameter measured by LIGO was very weak. So if you don't take that into account, if I allowed for formation of 85 solar mass black holes in my model, formation of GW 190521 would be very, very typical channel, binary evolution channel, common envelope channel, which were proposed many years before any LIGO detection. Okay, so this would hinge on uncertainties in stellar evolution and reaction rates of carbon burning. Okay, so I would like to stop here, and then I just put a conclusion slide which give actual lessons that we go from 0102. So from 0102, we know that to form massive black holes, we need direct black hole formation that starts collapsing direct to black holes, and we need metallicity dependent stellar winds. We need also efficient angular momentum transport in massive stars. And from 03, I didn't mention that, but there's that one system that I skipped. We most likely need delayed core collapse supernova engine. Okay, that was to form object in the first mass gap. And for upper mass gap, we need decreased fusion rates and possibly enhanced mixing in our stellar models. But this only holds if all those LIGO events are coming from isolated evolution. If they come from global clusters, you would have a different slide with different lessons from global clusters. But I'm not going to touch on this today. Thank you very much.
Thank you, Chris. On behalf of everyone, I will clap for you. Okay, so if you have questions, you can now raise hands. And while you were doing so, I have...
Gopu has already raised his hand. Let him ask first.
I can't hear.
Yeah. Sorry, Gopu, just go ahead.
Okay, thank you. A very nice talk. I really appreciate. So I have a question about the 15 on, on 1905-21. So this has been reanalyzed by others, independent groups with a wider prior for the mass ratio very recently, and they came up with the argument that looks like this guy is not any of this, and I can't find anything wrong with that analysis. And that will put the one of the masses to be of the order of 150 plus. That will really put constraint on you, right? It will be impossible for you to make such a object.
Okay, so that's a case of so-called straddling binary. Straddling that you have both objects on the average side, on both sides of the mass gap. So when we go back to a classical mass gap, 1535, we take the total mass and put one black hole above 135 and one below 50, okay? That would be for me actually easier to make than what I'm proposing here, because stars are supposed to easily form black holes below 50 and about 135. So I did not personally produce black holes over 135 solar masses, but Michel Amapelli did, because I did not study stars massive enough to do that. So I need to change, stellar evolution, and I need to change reaction rates, sometimes go widely out of the, safety zone. But to get a binary like that, I wouldn't need to do anything. I would just need to extend my initial mass function. So far, my initial mass function go to 200 solar masses. But if I go to 300 solar masses or 400 solar masses, I would be forming black holes above 135, and I would be finding such systems. Does this answer your question?
Oh yeah, thank you very much. Yeah, okay. So the game is that But then the problem will be the unequal mass cases will be a problem for you, right? The
Yes,
extreme.
yes. So the mass ratio, I would have to then check if I produce enough of them to match the LIGO rate. That's a very good point. So that's probably a good exercise to do. I would have to put one of my students or postdoc on that. That's a very good point.
Thank you.
And you know what? I think we should be able to probably find answers to that in one of Michela Mappelli papers. She may have actually answered to that.
No. So this is a very recent analysis.
No. I know that. I know those analyses. I looked at those papers. But I'm saying Michela can have she had black holes of those masses claimed in those papers in her previous papers before LIGO detection.
Okay, I have not looked at those.
Yeah, she does have black holes like that.
Thank you.
All right. Any other questions? I have a question. Maybe I can ask now. So, Chris, you mentioned the full neutron star kick models.
Yes.
Can you update me on what is the status? I thought that full neutron kick models are ruled out based on the rates. Is that not correct?
Please repeat last sentence.
Is it still allowed based on the neutron star, and black hole rates that
Yes.
black holes can get full neutron star kicks?
So, it's a good question. So here I'm showing, like I said, if you look, let's say the left plot, red line, those are lowered by fallback natal kicks. So are low black hole kicks and kind of slightly smaller neutron star kicks. And magenta line are full neutron star kicks and full black hole kicks. So that if I take magenta models, full neutron star kicks and apply them to black holes, the rate for black holes will be too low.
Mm-hmm.
Neutron stars are given the same kicks almost in the both models. They will slightly go below the neutron star rate will drop slightly below 100 to be like 80. So it's close to 90% credible limits. You know, for magenta model, it will be 120 for red model. So I'm kind of above borderline. I have other parameters to bring them up. So, but if I give black holes, you know, heavy, high kicks, natal kicks, the black hole merger rates will be outside of empirical LIGO measurement. That's a fair point.
Okay, thanks.
Yeah, I just wanted, on this plot, I played with those kicks because I wanted to see, even if I go extreme and go from no black hole kicks to full black hole kicks, can I shift the distribution in such a way that I will match the blue points, that I will match LIGO data. And even with playing with full range of kicks, I cannot do that. Even if I'm breaking the rate limits. You see what I'm doing, is that right?
Yeah. I totally understood this figure. I just wanted to make sure that my understanding doesn't need to be updated.
Yes. It's correct.
Okay. Lankeshwar has a question. Lankeshwar.
Okay.
Yes, thanks very much. So about the upper mass gap, so you said that you can produce a black hole directly from stellar collapse if you take into account that different uncertainties in like convection or different reaction rates. Okay, so I just want to ask that those uncertainties, were they not previously known, or they were not just explored for some particular reason?
Okay, let me go to those uncertainties. People were fully aware, and some people, me included, we were asking people who actually do detailed evolution, do reaction rates, please provide us with error bars on the mass gap. And we could not get them to do this until the rumors that LIGO detected such a massive black hole appeared. So that's a very fair point. It would be way, way better if people did provide it, you know, assessment of those uncertainties and the influence on the upper mass gap, let's say 5 years ago or 10 years ago. It could have been easily done with MESA, easily. People just haven't done it because, you know, all the data was until, you know, 2019 consistent with black holes not being more massive than 50. But people did know that. So when you go, I can point you to those papers. And when you look at references that people use references when they study those uncertainties, like 10 years old papers. Okay?
Okay, thank you.
So, Saurav, there is a question from YouTube. Should I read
Yeah.
it out?
Yeah,
Please.
please do.
Okay, so Chris, so we have a question. It says that what fraction of POP3 stars became black holes and neutron stars? Given their mass is high compared to the population 1 stars, how does it map to Marder rate density curve?
Okay, so this is a question that seems to be confusing in the people seems to be confused in the community. So that I need to make 2 points. One about masses being, much higher in population 3 stars than population 1 and 2. This doesn't have to be true. That was the picture 20 years ago, maybe 15 years ago, when people didn't see much of a fragmentation of a pristine gas. So they thought that stars in population 3 would be very massive. But they corrected several stuff, and momentum transport in the dark matter halos and collapse of the molecular clouds, and they do see a lot of fragmentation. So all those stars may be, on average, slightly more massive, but not much more massive than POP1, POP2. So you don't expect much of a change. But let's take that, even if you take that into account, there's much bigger issue that wipes that out. Even if you had much more massive black holes and neutron stars from POP3, there's a different thing. Let's look at this plot, which shows the redshift distribution of the merger rates, okay? So those are for POP1 and POP2, and those stars peak at redshift 2. Therefore, and then the rate drops because the production of stars of POP1, POP2 drops. So the rate is dropping down. If you plotted the same curve for POP3, which I have a papers on that, exactly the same plot for POP3, they would peak, the merger rate density for a double black holes or a double neutron stars for POP3 would peak at redshift 10, at somewhere at that level. And then they would drastically drop down to redshift 0. It would be almost at, they would be almost at nothing. It would be about 3 orders of magnitude below LIGO empirical merger rate estimates. And that's due to the fact that usually delay times between star formation and formation of double black holes and the mergers are pretty short. So you follow star formation. And we know that population 3 stars happened before, reionization around, redshift 10 or so, or even it was peaking. It was started earlier on, even at redshift 20 or even, redshift 30, but it peaked at 10 and then declined rapidly. Okay, so that's my answer.
Any other questions from YouTube, Shruti?
No, that was the only one.
Okay. So thanks, Chris. We had all the questions, and thank you for giving this talk. And bon voyage to Brazil.
Thank you very much for inviting me. It was fun to give the talk. It's really, we're living in a really good times to do, gravitational wave astrophysics right now.
Yes.
And actually, I'm very happy I lost the bet with you because life is more interesting that way.
Yes. And we should meet in some conference after the craziness is over and talk about probably completely new demographic of gravitational waves by then.
Exactly. Okay. See you guys. Thank you for listening and for all the questions. Goodbye.
Bye-bye.
Thank you. Bye.
Thank you.